So from the 2000s to today, we've seen the development of a suite of technologies. During the 2000s, it became apparent that CT technology was not the sought-after silver bullet that was going to eliminate the fluid tailings challenge. Suncor experienced difficulty placing the CT deposits subaqueously in a deep water environment. And this resulted in fines segregating from the coarse tailings. Syncrude experienced operational issues due to conflicting objectives. Increasing the water content of the coarse tailings is required to get higher bitumen recoveries, particularly in a high fines ore body environment. But the increased water content also results in a higher degree of segregation in the CT deposit. CT requires a large containment volume because it's mostly sand, and it uses the sand, which is also in demand for construction of the containment. So for these reasons and the operational difficulties, Suncor ceased CT operations in 2009 in favor of other options. Syncrude continues with CT operations, employing a Tremie diffuser for their deep water deposit to minimize subaqueous segregation. A second generation of CT plant was recently commissioned at the Aurora mine site. So the challenge was this growing volume of fluid tailings, which, as I say, grew from 500 million to a billion over the past 15 years or so, and a projection of an increased growth. So the challenge was to develop a suite of technologies to manage this volume growth and prevent its build-up beyond a reasonable level, so that all could be incorporated into the final landscape and fit with the end-use land requirements. So the challenge, find solutions that effectively optimize both environmental and cost performance, dewatering the fluid fine tailings, treatment of the process-affected water, and reclamation of the tailings disposal areas, both in a terrestrial and an aquatic mode. Two approaches are used for managing fluid tailings. One is to recombine the tailings with the sand, and the largest of that is the sand beaching operations that naturally capture a portion of the sands. Generally, in most cases, over half of the fines are easily captured in that manner. The other is the composite tailings that I had described, which is either the method that I showed you, or non-segregating tailings is another version of similar technology, which uses thickened tailings from a fines thickener rather than MFT as the fines blending component. The other alternative is to go for separate management of the fluid fine tailings and make fines deposit themselves. MFT inline dewatering and thin lift fines drying is one of those techniques. A similar inline flocculation process and delivering the flocculated material to a deep deposit for self-weight consolidation is a second. MFT centrifugation and drying can either go into a drying bed or into a deep deposit, and similarly those three processes all use polymer flocculants. Extraction fine tailings thickening also uses flocculation process, but it takes the fines directly from the extraction process, so it's an integrated operation. We also have co-mixing of fluid tailings with overburden, and lastly, the water-capped MFT shown in the base mine lake operation, which can either be straight MFT or alternatively one could water cap thickened MFT. So here's how the sand cell and beaching operations work. The majority of dike structures in the oil sands are constructed from the sand themselves, the balance being from overburden and center reject materials. In the sand construction mode, cells are dozed up at the top of the structure, and sand poured in those to raise the dike, and then the subsequent cells are stepped into the interior of the pond, raising the dike in a sequential fashion. The beach runoff from the sand that's discharged to the interior of the dike runs down the beach and into the water zone where the fines settle, reaching about high 20% of solids after a year or so, and the recycled water being clarified on the surface. So one of the thoughts, of course, is to increase the fines in the sand itself. There are limitations on how much of this can be done, and it's important to look at the character of the fines that's being put into the sand structure. If too much fine content leads to very poor drainage conditions and difficulties in compacting, and it may also exceed geotechnical criteria for purposes of constructing the dike. So this is an area of great opportunity, but it's one that has to be done with care and a lot of technical oversight. Thin lift drying. Suncor and Shell have spent well over $1.5 billion on these drying operations, and this picture shows you the two operations with the small photos in the upper right showing the migration of the discharged flocculated material at 30% and rising to 65% at initial dewatering, and then if allowed to dry sufficiently, concentrations of 75% or greater can be achieved with thin lifts. Centrifuging. After 10 years of testing, Syncrude is commissioning $1.9 billion capital project for startup next spring. Basically, the MFT is put into the centrifuge with a polymer flocculant solution. Currently, gypsum is also used to improve the performance of the centrifuge operation. And that's a picture of one of the early trial deposits carried out on the site. The path to commercialization. This is a picture of the large-scale centrifuge plant. Construction is well underway. It will process fluid tailings from Mildred Lake Settling Basin, and it will start up in the spring. The thickened tailings process. The thickened tailings process takes the flotation fines from the extraction process, which is basically a desanded stream of tailings, and feeds that fines-rich stream into a thickener with polymer flocculants. Then the underflow is at anywhere from 45 to 55% solids, is pumped to an area for further drainage and dewatering. That's a picture of the jack pine thickener at Shell's jack pine mine, the third of 3 thickeners installed by Shell. Accelerated dewatering. I mentioned earlier that one of the processes is to flocculate the MFT from the tailings settling basin and put it into a deep deposit. This is a photograph of a test that was done in 2009, where the material was put into a 10-meter deep containment structure with a decant structure it's pre-installed in the basin, and very rapidly filled in about 6 weeks. And you can see the material being discharged, and a year later it's dried and cracking on the surface. And in this particular case, rim ditching was used to develop a surcharge load on top of the deposit. And we have David Carrier sitting here on my left corner, who is the originator of that process in the Florida phosphate industry. I mentioned co-mixing of overburden and fluid tailings, and this could be done with straight fluid tailings from the tailings pond, or it could be mixed with centrifuge cake to produce a freestanding material. And the trick there is to get a good blend of the material with a material like Clearwater clay, which is an over-consolidated clay material that can absorb some water, and control of water content and the resulting strength of the material is the key operational factor. Then we have cross-flow filtration. This is Dave Seco's championing of this process. How it works is tailings is pumped through a porous pipe. A sand bed generates a self-filtering media on the perimeter of the pipe, and the slurry is dewatered before it reaches the tailings pond, so that a non-segregating mix is achieved through lower water content in the slurry. And then most of the fines are captured in the sand deposit, and this results in a much reduced need for settling and containment. Key milestones on this process are that the pilot facility is constructed last year and this year, and plans are being developed for a larger scale pilot next year. An interesting challenge for hydraulics with that process. Water capping, 25